Hi everyone, this is the first video of week 15. So this week we're going to go over three chapters in two chapters very briefly and quickly, and the last chapter, chapter 16. So in two video clips, I'm going to go over chapter 12 and chapter 14. Chapter 12 is bolted connection. Chapter 14, welded connection. Both are related to the connections, right? So I combined those two chapters into one slide, and I already posted on the Blackboard last week under week 14. So I'm going to go over chapter 12 today, going through the slides and briefly explain about the bolted connections. Bolted connections, we already touched most of the things in the tension design. So we already know how to estimate and include those bolted connections in tension members. So I'm going to extend more discussion on that. And then chapter 14 is about welded connections. Um, so I'm going to briefly explain about the welded connections in the separate video. And then we're going to move on to chapter 16, which is the last chapter of this class about composite beams. Okay, so I'm going to share the slide. Here we go. Okay, so in this PowerPoint, I'm going to touch both bolted connection and the welded connection. Before I jump into those two connections, let me talk about the role of connection in steel design and how we assume the connections will behave and how we assume the connections will impact our analysis of the structures. This is very important to understand how these connections will behave and use in our analysis, because that will determine the strength of each member. And for example, we talk about the column. In the column analysis and design, we use effective length factor that is based on the boundary conditions, right? And that boundary conditions in reality is going to be related to the connections. And so I'm going to talk about these two, shear connections and moment connections, in a minute, but that's how we can classify the connections in general, uh, combining both the bolted connections and welded connections. So brackets is kind of a typical um, kind of connector used in the steel construction, and we can both use in the bolted connections or welded connections, like a bolted brackets or welded brackets, how we can attach that bracket into the bigger member through bolts or welds, right? So this is kind of the thing. So here you can see the brackets welded to the column, right? And this bracket will connect to the beams like this. That there is another one here. So I think this one is attached to the web of this column, and that will connect this column to the beam. So those are kind of the real world examples. Okay, so let's talk about the beam to column connections. And here we have two classifications: moment connections and shear connections. So let's talk about how we can classify the connections into shear connections or moment connections. Basically, shear connections is more simple connections compared to the moment connections. So these are four examples of shear connections. So for example, this is a column and this is a beam. So we connect these beam to the column through these angles, and this is only one side, but we can assume there's another angle on the other side. So that's why we call the double angle connections. Or we can just use a single plate, which is attached to this the flange of the column. So this shear tab will connect this entire column to this beam. And sometimes we use a bolted connections mostly, but so this is another example. Here we have a small angle, top and the bottom, that will connect this column to the beam. And very similar, but instead of having just simple angle here, we have a small kind of bracket. So this beam is sitting on top of that bracket. Okay, so these are the examples of shear connections. Before we go on to the next slide, I'm going to move on to the examples of moment connections. So these are 4 examples of moment connections. As you can see, moment connections are more stringent, right? So for example, here we have just shear tab like the shear connections before, but this one is kind of stronger. So shear plane, the shear plate, moment connection at the flange, and this is another example that we have a very similar shear plate now welded on the web of this column. So that's why we call the shear plate moment connection at the web. And this one, earlier we have only just top and the bottom with small angles, but now we have more, you know, powerful and stronger connections. So basically, these moment connections will resist against the moment, which means these connections will transfer the moment, which is, you know, provided by this this beam. So the moment will be transferred through these connections from the beam to the column, while the shear connections, because these connections are too simple, we assume that these connections will allow to have a rotation at the connections. So this is the kind of a definition of the shear connectors. The goal of the shear connector is for the angles to deform enough to allow the joint to rotation, right? So again, this is example that here we have a column, we have a shear plate connected through these bolted connections to the beam or from girder. So this is a big beam, right? So this is girder, and here we have a small beam through these angles, double angles. Okay, so let's think about the failure mechanism of it. So let's just imagine here we have a girder to interior beam connections through these double angles. Then first of all, so we have to think about the failure mechanism of everything. So we can think about the failure mechanism right on the bolt itself and about the smaller one, which is the beam. And then these are the failure mechanism at these double angles. And each one, for example, these angles are attached to the web of this big girders. On there, we can think about several different failure mechanisms like these. Block shear failure, of course, and shear yielding and tear out around the bolted connections, and the bearing failure around the bolted connections. I'm going to talk about tear out failure and the bearing failure in a minute. And we can do the same failure mechanism on these angles. So these are all possible failure mechanisms, and as a designer, you have to go through the capacity and demand check for all these against all these failure mechanisms to make sure your connection is safe enough. Okay, so how can we classify these, you know, the connections as it is, whether a moment connection or the shear connection? It is all depending on the behavior, because there's no such thing as 100% moment connections or 100% shear connection. So when we look at the relationship between moment and rotation, okay? So for example, with a given moment, here we have a given moment, this curve A will provide very minimal amount of the rotation, while this curve C will provide a lot higher amount of the rotation compared to curve A, right? Let's just focus on these two relationship. So when we apply the moment to the moment, the beam column connections, and we measure the moment and corresponding rotation with the amount of the moment. And then let's say we set the amount of the moment and compare the amount of the rotation. So curve A, you can see that we have a very high resistance against the moment that will provide a very little amount of the rotation. So that is the typical characteristics of moment connection. Because we will transfer the moment, we have a resistance against the moment that will provide very minimal rotation. While this curve C is kind of opposite, right? We intentionally allow the rotation. That's why we have a lot higher rotation with a given amount of the moment. So that is classified as a shear connection. Minimal moment, free to rotate. And curve B is kind of in between. So anytime we classify it as a moment connection and the shear connection, in steel design, we also call it as a fully restrained and the simple is a shear connection. In between, we call it partially restrained. So fully restrained is kind of a moment connection, okay? And the simple connection is the shear connections. And in between, this is curve A, B, and C, right? Curve B was in between. That is classified as a partially restrained. So those are another terminologies that we use in the steel design. Okay, let's talk about the high strength bolt. In general, we use very high strength material for bolt itself because we'd like to make sure that the connection has a higher strength than the other connected members so that we do not have a failure at the connection portion. That's kind of a main idea. So here you can see we have 325 steel or 490. Those are high strength steel. And table J 3.1 in your steel manual, they provide all the material properties in tension and shear. Looks something like this. Okay, so this table is directly coming from table J 3.2 in your manual. Two different types of the bolt. This is very typical high strength bolt. So here we have a shank and the threaded area. And this is a very special bolt called tension control bolt. So we have to have a special device to fasten this type of the bolt. But the good thing of this tension control bolt is that when we reach to the target strength of this bolt as designed, and this tip of the twist of tip will be removed automatically. So we can guarantee that all the bolted connections and all the bolts will maintain the same level of the strength. Okay, you can easily Google the tension control bolt, and you can see a lot of different kinds of tools and the device in how they fasten the tension control bolt. We already talked about the bolt size, right? So I'm going to skip that. The limit states for the bolt are the bolt shear and the bearing on the material behind the bolts. So we have the tear out failure and the bearing failure. And also we can think about the tension in the bolt, depending on how we connect those bolts in the connections. So this is the case for the shear failure. Depending on the arrangement, we can think about the single shear or double shear, depending on how many shear planes we can recognize. And we already talked about it in this the strength of material, right? And double shear case, we can have a twice amount of the capacity for the bolt. So this is how we can calculate the strength of the bolt. Typically, very simple equation, Fn, that is the strength of the bolt coming from the table J 3.2, and AB, that's the area of the bolt in the shank portion. And depending on the design philosophy, LRFD and ASD, we have two different factor, right? The phi factor for the bolt strength calculation is 0.75, and the mega factor for ASD, that's always 2.0. So this J 3.2 table is kind of important to estimate the capacity of the bolt. And we have two different the failure mechanisms. So one in that when the bolted connection is going to be under the tension. The second column is going to be the bolt is failed in shear. Okay, and depending on the material properties, 307, 325, and 490. And here we have two different cases when the threads are not excluded from shear plane or are excluded from the shear plane. So for example, let's say here we have a single shear case and we apply the shear forces, and this is the bolted connection. Okay, so let's say the threads are only here. That means the threads portions are excluded from the shear plane. Shear plane is, in this case, this line, right? So if that's the case, we're going to use, for example, these two. So we're going to use 60 KSI. If the shredded portion is not excluded, which means included in overlapped with the shear plane, then our capacity is going to be reduced to 48. So that's how we can determine which strength is going to be used. Under tension, these are not, doesn't matter, because under tension means when you have a bolt, we're going to apply this force in this way, right? So whether you're the the threads are included or excluded from the shear plane doesn't really matter. So that's why we use the same value. Anyway, so that's how we can read these numbers from the J3.2 table. And these are two failure mechanisms for bolted connections. One is a tear out of the plate. So if this bolted connection is too close to the edge of the plate, that means in that case, we can expect to have a tear out failure. Otherwise, we could have a bearing failure, right? So the failure it is not totally torn out, but we could have the reduced capacity due to the distance between the edge to the bolt. So here we have two equations to calculate the capacity. Again, this is for tear out failure, and this is for bearing failure, very similar. Okay. And again, we're going to use the values from this table 3.2. So this slide summarizes all the equations for the capacity calculations for bolted connections. When the bolt is going to be in tension, this is the equation. In shear, we have to use these two equations. For tear out of the bearing of these plate failure, then these two the equations will be used to figure out the capacity of the bolted connections. Okay, so I just briefly went over the the characteristics and descriptions of the bolted connections today. And next time I'm going to talk about the welded connections. Again, very briefly, I just want to explain and introduce the topics and the different kinds of the welded connections next time. And then we're going to move on to the last chapter, chapter 16. Okay? All right. Thank you and see you later.